You got it? All right, I'll begin. Dear Heavenly Father, we thank you for this day. Thank you for these students. Just pray that you be with us today. Help us to, again, Lord, glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so hopefully you guys know a little bit about isomorphism now. So what is an isomorphism? Isomorphism is what? If you have a mapping psi that goes from, say, vector space V to vector space W, V and W vector spaces over some field F, then what does it mean to say that psi is an isomorphism? That means that psi is what? First of all, psi is a linear transformation from V to W, right? Second, psi is an injection, right? Let's see here. A convenient way to measure that is to check what's the kernel. So if the kernel of psi is the set just containing 0, which, by the way, sometimes we just write as 0 to be lazy. That will, given that it's a linear, if the kernel is 0, it's injective. Right? Prove that. And then 3, of course, we do need that psi is also surjective, or onto. Now what that means, of course, is that the range of psi, right, which we could also write as psi of V, well, that's just equal to W. Now, so that's what it takes. Now, 2 and 3 collectively make psi a what? All right, this makes psi a what? Nah, well, true, but more to the point, bijection, right? Bijections are invertible, though, that's true. So psi is a bijection, because it's an injection, which is also a surjection. So this is what's meant by isomorphism. So I need to clarify a few things in your homework. I'm not going to do that with class time, though. What I'm going to do is I'm just going to go through the homework and rewrite it again. Not to change the problems, but just to add detail to the problems. I've given you formulas for a few linear transformations, but then I've neglected to say, here, for example, here's the ambiguity, current ambiguity that you might be suffering from. If I have t, right, and it's a linear transformation, say, defined as follows, t of f of x is equal to, say, f prime of x, right? And this is for f of x, an element of, I don't know, P2 R, right? Possibly degenerate quadratic polynomials. Is this a surjection? Is this mapping onto? The answer is, what do you mean? You see, I can't answer the question of whether this mapping is a surjection until I first answer the more basic question of what's the domain and what's the codomain, right? The codomain would seem to implicitly be P2 of R, right? So there's a couple different ways this could go, right? On the one hand, you could say, well, T, a mapping from P2R to P2R, right? So one interpretation would be this. And that's definitely not a surjection, right? For example, x squared is not an element of the range of t. Because if you differentiate a quadratic polynomial, you can't get back something with x squared, right? So that's not in the range, therefore it's not onto. But on the other hand, right, if I was actually meaning, let's say, t is a mapping from P2R to P1R, well, you see then, it is a surjection. So I've asked you a few questions like, is this a one-to-one, is this onto, or is this a surjection, right? But I neglected to tell you the codomain of a couple of the things in the homework, and so those questions are ambiguous as they're stated. I'll fix that and repost it today, okay? If everything goes as planned. This actually is an interesting example. We'll use this, all right? We'll use this to illustrate the ideas today. I'm going to come back to this. I think it's a nice example. So what I want to talk to you about now is the problem of the matrix of an abstract linear transformation. All right, so here's the data that we have. We're given a vector space V with basis, let's say V over a field F with basis beta. Let's say that beta is V1, V2, Vn. And we're also given a vector space W over a field F with basis gamma. And let's say that gamma is, I don't know, W1, W2, Wm. Right, so we got two vector spaces, one with basis beta, the other with basis gamma, and these are finite dimensional vector spaces. The dimension of V is what? What's the dimension of W? What's the dimension of V? Can you guys tell me? Right, V is N as in nanu, and W is M as in mommy. All right, so N, M, because you can count, right? It's the number of vectors in the basis. All right. Now what I want to do is I want to study a linear transformation that goes from V to W, all right? So consider, let's say T, an element of the linear transformations from V to W. What I'm about to do is to define, all right, how we can write this in terms of a matrix multiplication. I did an example of this in part 3 of what I posted, right? But I'm just going to come back and define it again here since we're all together, and some of you may not watch that. All right, let's see here. Okay, so here's the picture, and the picture is useful here. So we've got, here's a vector space V, all right? Then there's this linear transformation T. T takes us from V over to W, all right? I guess if the homework hadn't distracted me, what I would have said at the start of class today, what I should have said, what are very, very important examples of isomorphisms? If you'll allow me just to squeeze a comment back in here. Example. How about this? If we take phi beta of V equal to V beta, where beta is basis, right? For vector space V. And, so phi beta is what? Phi beta is a mapping from the vector space V to Fn. So this is called the coordinate chart with respect to the beta basis. It's an isomorphism of the vector space, a finite dimensional vector space of dimension n to Fn. Probably the most important isomorphism that we study, the coordinate map. Sorry, my red pen is kind of sad. Oh man, I got no other red pen. Oh, stink. Oh well. Sorry, I'm just saying phi sub beta. I'll write it bigger over here. So then we've got two maps. And we got down here we've got, let's say, Fn. And then over here, you have Fm. All right? So there's a coordinate map that goes from V down to Fn called phi beta. This takes in abstract vectors and spits out column vectors. It's the coordinate mapping. In fact, You didn't realize it at the time, but you proved this was a linear transformation in one of your homeworks, right? Because I had you show that the coordinate vector of cx plus y was equal to c times coordinate vector of x plus coordinate vector of y. Remember that? You've proved, in fact, that this is a linear transformation. And it's easy to see that that's injective, because if you look at its kernel, the question is what vector has what vector has coordinate vector 0? Well, the only thing that has that is the 0 vector, right? So its kernel is 0, so it's injective. And it's not hard to see it's also surjective. This is an isomorphism. Now, okay, so on the other hand, over here, you have the gamma, see, because the gamma basis lives here, whereas the beta basis lives here. All right? You also have inverse maps. You can go the opposite way, right? You can go like this direction with so-called phi beta inverse. And you can go this direction like this with phi gamma inverse. Those are options that you have. Okay? So the so-called matrix, all right, of the linear transformation T, we get down here. So this is going to be left multiplication by the matrix of T beta gamma. Beta for the domain, gamma for the range. So I'm defining what I just wrote in pink down there. How do we define that? Maybe be more explicit. So L of T beta gamma is equal to, and what we do, all right, is the picture tells us how to define it. So the picture is, instead of going this way, which is the thing we're trying to define, we use the coordinate maps to follow this path up here like this, right? See? Just follow the diagram like that. Now, composition is a funny thing. The thing that goes first in the diagram goes last because we write function composition. So I start with phi gamma, right? Phi gamma, all right? Then T is in the middle, and then phi beta inverse. And that's function composition there. See, so I go this way. I go opposite. I trade my column vector for an abstract vector in V. The linear transformation T goes from here to here. And then from W down to Fm, I use the coordinate map phi gamma. By the way, definition, L sub A, right? This is, well, let's see here. L sub A of x is equal to AX, right? For all x in Fn, and here A is in Fm by n. This is just the matrix, the linear transformation, which is induced by multiplication by A. So when I write L sub T beta gamma, I'm saying this is the linear transformation of column vectors, which is obtained by multiplying by that particular matrix. What's that? Yes, indeed. Now, of course, you could say L itself is a mapping, right? From F m by n to the set of linear transformations from Fn to Fm, right? And this mapping L, it takes what? It takes A and it maps it to L sub A. L trades a matrix for a linear transformation. Yep. Is it possible to trade a linear transformation for a matrix? Yes. That's the standard matrix map. Yeah, the inverse of this is just the process of finding a standard matrix from a given linear transformation. In fact, this is an isomorphism. There's an isomorphism between the set of m by n matrices and the set of linear transformations from Fn to Fm. Yep. Is the definition in green for the what? This is a separate definition, sorry. No, I need to use this notation. I talked about that notation before, but I need to bring it up again. This, on the other hand, is a separate. I'm using this multiplication by a to up here for this, right? I need that notation to make the other notation, definition rather. Now, you could write this a different way, right? So this is one definition. Equivalently, what could you do? I can't spell equivalently. So what does it mean if the left multiplication, this transformation here is left multiplication by that matrix, right? So in other words, I could say that T beta gamma is what? It's the standard matrix of this thing. You could also say that would be valid. That makes sense because why? Because this mapping, right? This phi gamma composed with T composed with phi beta inverse is what? Mapping from where to where? It's a mapping from Fn back to Fm again, right? So that's a linear transformation on column vectors. How do I know it's a linear transformation? I assume T was linear. The coordinate maps are isomorphisms, which means they're linear with linear inverse. So we have a composition of linear transformations, which is once more linear. Now this is kind of nice, but there's yet another way. Or if you don't like this, if you take, let's see here, how to write this. I don't know, there's about 13 different ways to write this thing. Let's see here, if I take, I don't want to do that. Now, it's easier to see in the diagram. So another way, if you don't mind, I'm going to erase the inverse for a second, so I can have some space to work here. Man, I wish my red was working. Oh well. You could go like this, right? Or you could do what? Alternatively, you could do what? You could go like that, right? Oh, thank you. Sweet. Wait, I'm not allowed to say that. Let's see here. So what we got? Going from here to here, what is this map? T composed with what? Phi beta inverse, right? What's this map down here in the orange? It's left multiplication by T beta gamma. That come first or second? That comes second, right? I mean first, rather. So that's composed with what? Phi gamma inverse, right? So you could write, actually I don't like that either. Sorry. I mean, fine. What did I just say? Phi gamma inverse. You could do that. That's actually not what I wanted. What do I want? Oh, who cares what I want? Let's go on. Sorry, I mean, there's like 13 different things you can get from this. So the one thing I'm looking for, and I'm not seeing at the moment for reasons I don't entirely understand, I want this formula, right? So, and let's see, maybe you guys can explain to me how this is true from the picture. So one thing you can say is that t beta gamma, all right, times a coordinate vector of v with respect to the beta basis is in fact equal to t of v, all right, with respect to the gamma basis. Like that actually is how I tend to calculate the standard, not the standard, but the non-standard matrix rather, t beta gamma. How would I see that this formula is true from these other things? I guess I just have to express it. I have to like translate this from the coordinate maps, right, back into the phi beta and phi gamma notation. So let's just do that. I think it's maybe a useful exercise for you guys, and maybe me too. Ooh, thank you. An excuse to use this. Let's see here. So this is left multiplication by t beta gamma, and then that's acting of this, right? Which is what? That's of phi sub beta of v, right? And that's equal to what? That's equal to phi gamma of t of v. That's just this formula in another notation. That's all it is. And you can see then that being true for all v is what? This is really just saying L of t beta gamma composed with phi beta is equal to what? Phi gamma composed with t. So can you guys tell me how I would have seen that in the diagram? Like chasing things in this diagram. Could you see it? Let me erase this and see if we can see it. How about this one? We start with phi beta, right? You start here. This is v, right? And so that maps us down here to what? V beta. And then over here, right? So like this is exactly that, right? And how about the other one? Yeah, we start with v, right? Yeah, t of v. And then down here, we get t of v gamma, which is, by the way, phi gamma of t of v. Okay, so this round trip here, call it star star, corresponds to this formula over here. All right, I'm sorry if this is confusing to you. I'm not after anything in particular. What I'm trying to show you is just how this diagram works and how you can see different relationships in it if you just study the way the arrows go. And you can, like for example, if I wanted to compare what this coordinate transformation looks like relative to another one, it's not much more work, right? But before I do that, let's just take a breath here and work an example. Let's look at this example in particular. Simple example, right? But we have t of f of x equals to f prime of x, right? And here I'm going to say t is going from the span of, let's say, x squared x. Can't write. X squared x and 1. And what do you guys want to make the codomain? I'll be boring. I'll make it x squared and x and 1. All right, so maybe that's not useful. It's probably better if I do the second case. That would actually illustrate a little bit better what's going on. So I'm actually going to choose 2. And so I'm going to make the codomain not the same thing again. Okay, so What's a good basis for P1? How about x and 1 maybe? Okay. So here it goes. My typical strategy. I look at f of x equal to ax squared plus bx plus c, right? I let t do its thing. That gets me over to what? T of f of x, which is what? 2ax, right? Plus b. What we're trying to do right now, guys, is to find the matrix of the linear transformation with respect to the basis. Now, I didn't tell you which basis, did I? Sorry. What do I mean? Let's call this set right here gamma, okay? Good grief. Beta. Let's call this one over here gamma. Are those linearly independent? Yes, they are. You prove that monomials up to some particular order is linearly independent. That's one of your homework problems. And do they span? Well, that's how I define the spaces, so yeah. They're definitely linearly independent spanning sets, so they're bases. Great. Now, you guys, we have to figure out what is the coordinate vector of v, and I mean of f of x in this case, and also t of f of x. So here we go. So what's phi beta do? What's the coordinate vector of this? Well, it's just a, b, c, right? That's f of x beta. Okay. Just noticed you're missing your shoes. Let's see here. I will try not to be distracted by barefooted students. Let's see here. And then let's see here. This is phi gamma what? Yeah, so you have what, 2a and b, right? That is, in fact, t of f of x, the coordinate vector of the image with respect to the basis of the codomain. All right? And then, so I'm looking then, this is left multiplication by some particular matrix, right? T beta gamma. And what is that? Oh, I ruined my example too. Let's see, this is going from what dimension to what dimension? 3 to 2. So I'm looking for a 2 by 3 matrix, all right? 2 rows by 3 column. So I've got to take A, B, C, and have to get out 2A and B. And then I just fill in the blanks, basically. That's why I like this particular formula, like this one right here. This is the one I'm really using. So, okay, so what do I put? I got myself a, 2, 0, 0, and 0, 1, 0, yeah. And there you have it. So that's one way you can calculate the matrix. Now, if you look at this and you just kind of go back and use basic matrix theory stuff that we already know, another way you can look at this is that T beta gamma, it's nothing more than the matrix, like it's T of V1, the gamma coordinate of that, and then it's T of V2, and the gamma coordinate of that, and then it's T of V3, the gamma coordinate of that, where V1, V2, and V3 are the B. I'm saying beta is equal to V1, V2, V3, just for the sake of like connecting with the general idea over there. So that's another way. You can just calculate the coordinate vectors of the basis, the image of the basis in the domain, and that will give you. And so like this is another way we could do it. So what's the image? What's the image of x squared? 2x, right? What's the image of x? It's 1, right? What's the image of 1? 0. And so you see what we get. 2, 0. Wait a minute. Yeah, 2, 0, 0, 1, and then 0, 0. It's another way to see it. I do like that second way also. Let me use this. Let me use the second way just to, same problem. So this time, let's suppose we're going from P2R to P2R. Again, T of f of x is equal to f prime of x, okay? And then I'm just going to use, I want to calculate T beta beta. All right? So just getting straight to the point, what this is this is T of x squared, and the beta coordinate of that, T of x, the beta coordinate of that, T of 1, the beta coordinate of that. Of course, I understand where that formula is coming from in terms of the picture, but that's a nice, relatively fast way to calculate the matrix, right? And here, of course, beta I'm using. I'll tell you what, this time I'm going to do it 1x x squared just to be different. How about that? I did it x squared x1 last time. So I'm just turning the order around, see how it changes things. What's the derivative of x squared? Well, it's 2x, right? And then I've got 1. And then I got what? 0. This gives me what? So just to emphasize, 2x is equal to what? It's equal to 0 times 1 plus 2 times x, right? Plus 3 times x squared, listen to me. 0 times x squared, right? That's how I know that the coordinate vector of 2x with respect to the beta basis is 0, 2, 0. That's my thought process, right? Remember what the coordinate vector is. We rip off the coefficients from the linear combination, which builds the vector in question with respect to the basis in question. So like this, so what I got is I got 0, 2, 0. Can you guys tell me what the second column is? One, 0, 0, okay. And the third column, of course, is zeros. And there you have it. My first example was a surjection, right? Because the range is two-dimensional, and the image, the codomain is two-dimensional, and you know what? So was the range of the mapping. Over here, on the other hand, the codomain is three-dimensional, and yet you can see, well, that's the thing. I'm claiming this is enough for me to see that the range is two-dimensional. But you see, I'm using a theorem there that I haven't yet really explained to you guys, which I should. Before I do that, though, what should happen if we look at the matrix? What would the matrix of T squared be with respect to the beta basis? That's T composed with T, right? We have a wonderful theorem which states that this is, in fact, just this. So, you can multiply, right? What do you get? Let's see what we get here. Looks like I get a 2 there, right? And what else do I get otherwise? Do I get a 2 again? Is that right? I think I get zeros, but you guys help me out. Did I do it right? 2, 0, 0, then what's next? 0. It seems like I get 2 again, huh? And then what? 0, and then zeros. All right. What happens, and what do you think that would be? Oh, man, time flies when you're having fun. So how about this? If I look at S, right? S of f of x equals to what? How about f prime prime of x? What would that look like? S of a plus bx plus cx squared, right, is equal to what? See, I've made a I've done something wrong. That should be 2c. So that if I differentiate twice, I should not get that again. I've made a mistake here somewhere, guys. Where was it? Good grief. Are you kidding me? Oh, man. Okay. 1x x squared. One x squared. There we go. See, I can see from this that S beta beta should be 0, 0, 0, excuse me, 2. All right. And now, if you calculate this, what do we get? Zeros, right? Zeros, and a 2 in the upper corner. As we ought. Because if you take 2 derivatives, you get this matrix. This, by the way, if I am asked to come up with an example of a matrix which is nilpotent, I immediately think of this example because I know if I differentiate a polynomial a couple times, it's going to be 0, right? So like I know that the matrix of the derivative acting from a, say, P2 to P2, I know it's going to be a nilpotent matrix because I know the transformation is also nilpotent. In other words, if I compose it with itself a few times, I'm going to get 0, even though itself it's not 0. This is nilpotent order 3, I think. You do one more time, you get 0. All right. Now, I guess I have to admit defeat and use the projector. I'm sorry, guys. I have no regrets. I think I've gone through things slow enough up to this point that you should have understood what I did so far today. And what I'm about to show you is just simply an extension of the thinking I've already illustrated for you. There are beautiful theorems which relate the matrix of the transformation to the transformation itself. So, for example, if you look at this, right, the basically whatever, there's a connection between, for example, the how do we define the rank of a linear transformation? The rank of a linear transformation is the dimension of its range, all right? How do you define the nullity of a linear transformation? The nullity of a linear transformation is the dimension of its kernel. What's the connection between the kernel of the like the nullity and the rank of the transformation versus the nullity and the rank of the matrix which represents it, given a choice of basis? They're the same thing. Nothing could be exactly just the names are not like some kind of sneak attack on your studying. Like they're legit. They line up. So we can use the matrix of a linear transformation as a tool to study the structure of a linear transformation. No, nobody wants to see that. Let's see here. You want to see it? Come on. Where you go, you stupid thing. There's so many things I want to tell you. My goodness. Goodness gracious. These are the big ones that I was just mentioning. So suppose you find yourself faced with the problem of understanding. So I mean, here's just sort of a generic problem. Given S subset of some abstract vector space V, is S linearly independent? What's an approach you can take to this problem? I mean, there's a couple different approaches. You could attack it directly, right? Say, well, I just set a linear combination of the vectors in S equal to 0 and try to see, one would be just direct calculation. Sometimes that's the way to go from the definition, right? And try to show the coefficients are 0, right? That's one way we could go. But there's another way now, right? If V is a finite dimensional vector space, another thing you could do is you could study, what could you do? You could study phi beta of S, right? Now this would be a subset of Fn. So I'm assuming here that the dimension of V is equal to, n. It's a vector space over F. So given a set of abstract vectors, you could feed it to the coordinate map, right? And out would pop a corresponding set of coordinate vectors. You can then study, are those coordinate vectors that are linearly independent or not? If they're linearly independent, guess what? The corresponding set of abstract vectors is linearly independent, and vice versa. Now I know that linear independence and linear dependence is preserved by the coordinate mapping because the coordinate mapping is an isomorphism, right? Which is linear transformation, which is not just a linear transformation, it's a linear transformation which is, one-to-one and onto. So it totally preserves the story of linear dependence or independence. That's a very nice thing, right? Because down here, we just face a set of column vectors, right? So if you got some nasty abstract question, you can just feed it to the coordinate vector and you have a corresponding problem in column vectors, which we know, nice matrix calculation techniques for. And that's essentially what this lemma is about, is just that the null space of the linear transformation is actually the image of the kernel. So like in that picture I was drawing a second ago, it would look something like this. So up here is V, right? Some subspace of V would be the kernel of T. Here's W. Some subspace of W perhaps is the range of T. Okay, T is a linear transformation from here to here. What this theorem is saying is that if you want to, you can look instead down here at the matrix of the mapping, L sub T beta gamma. Now there's a choice of basis there, fine, granted, but the image of this kernel T will be down here. That will be the beta of the kernel of T. The image of the kernel will be the null space of the matrix. Nothing could be more natural than that. The correspondence between kernels and null spaces. And likewise, guess what? The image of the range is what? Phi gamma of the range is what? You should know it even without looking at the screen. You can figure out what it's got to be. It's got to be the column space. What? What was that? The column space of T beta gamma. It's funny. All right? And if you study these arguments, it's just, there really isn't much to it except just working through the formulas that are defining the matrix T beta gamma. It's really much, it's not especially enlightening lemma to go through the details of. So what I'm trying to tell you is this is a useful thing for you to use in the homework. I've asked you questions about, is this mapping surjective? Is it injective? Is it invertible? Right? You are free to use this theory to help you out. So if you calculate the matrix of a linear transformation, right, and I asked you, is this mapping onto, right? If you can look at the matrix and tell either through some matrix calculation or just by inspection that, say, the rank of the matrix is 2, all right? And suppose the codomain is 3-dimensional. Game over. By this theorem, you can be like, oh, well, then this is clearly not a surjection, because for it to be a surjection, I would need that the range is 3-dimensional, yet it is clear that the column space is 2-dimensional, and the dimension of the column space must match the dimension of the range. All right, so we're able to, by inspection of or calculation from the matrix of linear transformation, we can see things about the corresponding kernel and range of the abstract in the most natural way possible. There is even a coordinate change. I guess I haven't really got. I'll talk about coordinate change some other day. What's that? Yeah, but it's really, it's nothing more than what we did today. It really isn't nothing any more than that. But I'll spend another day on it. You deserve, or you should be subjected to another day of it. I guess that means I'm still talking about stuff on the test come Wednesday. Sorry about that. Now, still here. You get to the point here. There's a natural question to ask, right? Well, there's lots of natural questions to ask, I suppose. But this stuff kind of goes together, so I'd like to talk about this while we're at it. So we have this, remember we had this stuff, we had this theorem before for a matrix. The number of columns in the matrix is what? It's equal to the dimension of the null space plus what? Plus the dimension of the column space, right? The rank plus nullity theorem. There is a corresponding theorem for abstract linear transformations. In particular, the dimension of the domain is equal to the dimension of the kernel plus the dimension of the range. Right? Now, one way to prove this is just through thievery, outright thievery. This idea that there's this one-to-one correspondence between kernel and null space and range and column space, right? So what you do is you just go, okay, I know the rank nullity theorem down here, chunk, and you just basically lift it up here, and you have it. That's the first proof I give. Cursor. Proof numero uno. So basically I say, okay, basically look at the matrix of the transformation. Well, we have rank nullity down there because we can count number of pivot and non-pivot rows, right? Columns, rather. And that gives us this. We prove that another day. But then we use that lemma to say, okay, so the kernel, the dimension of the kernel is the dimension of the null space, right? And the dimension of the column space is the dimension of the range. But the dimension of the whole vector space is n, so that's it. I actually here argue that you can map the basis for the kernel and the basis for the null space 1 to each other because the coordinate mapping is an isomorphism, so it takes basis to basis. By the way, I asked you to find some isomorphism for homework, right? What is probably the easiest way of finding an isomorphism? I mean, how do you find an isomorphism? What do you do? One way to do it is to find a basis in V and a basis in W. If they're isomorphic, there's the same number of basis things. So all you got to do is just map first thing in the first basis to the first thing in the other basis. And you just map basis to basis, extend linearly, and that's it. That's an isomorphism. The second proof is a standard proof of linear algebra, which I'll talk to you about here in just a couple minutes, and then we'll be done. So what you do is you take a basis for the kernel, all right? You extend it to a basis for the whole thing, which you can do because of our extension basis theorem plus minus theorem we had before. So I have like vk plus 1 through vn, which are not in the kernel. Then what you do is you look at the image under x of an arbitrary vector. You got two things. You got things in the kernel and things that are not in the kernel. The things that are in the kernel go to 0. And then you've got this, right? So that's an arbitrary image of the mapping T. It follows then that T of vi for I equals to k plus 1 to n, the things that are not in the kernel, the images of the things that are not in the kernel, they generate the image of the linear transformation. What we then do is I prove that this set tvk plus 1 through tvn is in fact linearly independent. If you suppose that you have a linear combination of these equal to 0, you can then show that it's, well, let me just right here. So if you set a linear combination of those equal to 0, use our lemma from the other day, write it like that. That would then say that these guys are in the kernel, right? But that's impossible because these guys were not in the kernel, and consequently, you have that this linear combination is equal to 0, but by linear independence of the basis, we get that ck plus 1 through cn is 0, which gives us linear independence of these images. But then you just count. So you've got the number of things in the kernel basis is k. The number of things not in the kernel basis is n minus k. K plus n minus k is n, rank nullity theorem. Bam. This actually is also useful because it shows you just the big story here. And this is kind of a boring story, but if you give me any linear transformation going from a vector space V to a vector space W, I can choose basis in the range and in the codomain, the codomain and the domain, that makes the matrix for the linear transformation just an identity with zeros. Right? And so that's kind of like generically the format of a matrix for linear transformation. You can choose a basis in the domain and the codomain to make it like so. But there's a fine print here. I'm assuming that we can separately adjust the basis in the domain and codomain. If we insist that we choose like beta beta, all right, same basis in the domain and codomain, you don't have such freedom. One of the homework problems I asked you about, if you could write the matrix in a certain way with a choice of there you don't have this freedom. And in fact, you'll find out the answer is no, you can't do that. There's a homework problem I asked you if you could put the matrix in a certain format. You'll find out the answer is no. Anyway, I digress. I'll shut up. Man, there's never enough time.